Welcome to tutorial 3.5 part 3. This is the last of the 3 tutorials from section 3.5 on empirical formulas. What we want to do in this tutorial is we want to move on from empirical to molecular formulas. So let me show you what I mean. Here's the work that we did in a previous tutorial for finding the empirical formula of a substance that is 80% carbon and 20% hydrogen. I don't want to re-go over this work again. This is just showing you the work. We came up with a formula of CH3 by dividing the masses, getting the number of moles of carbon and hydrogen that these masses represent, and then simplifying the ratio. The question arises is this now. Well, that's all good and that's all fine and well, but what if we know ahead of time that the formula of the molecule that we're interested in by this analysis is actually C2H6, it's not CH3. That's not the answer I came up with. I didn't come up with C2H6. I came up with the formula of CH3. The question is this how the molecule actually exists, or does it exist in some other form? For example, C2H6 is how it actually exists. How would I have known that? And the answer is at this point that the analysis that we've done so far with this combustion analysis won't get you to the actual formula C2H6. You have to have more information to get there. And the information you need is the molar mass. And let's see if this makes sense why you need the molar mass by kind of looking at this set of molecules. Look at all these molecules here. So here's a molecule. I've drawn it out without the kind of typical way we write them. This is CH3. This would be C2H6, C3H9, etc. But I drew them in this way with this kind of condensed structural formula so that you can see the point that each of these possible molecules that have an empirical formula of CH3 would in themselves be made up of these building blocks of CH3. So that allows you to recognize, I hope visually, that whatever molecule we have, the mass of that molecule has to be some multiple of what the empirical formula represents, 15 in this case. So stare at that for a minute and see if it makes sense. This thing weighs 15. To have the same ratio of 1 carbon for every 3 hydrogen, you could, for example, have 2 of those CH3 units. Well, then, of course, it would weigh twice as much, or 30. That tells you that the actual molecule's mass has to be a multiple of what the empirical formula represents as a molecule, as if it existed. All right, so let's look at that and make it nice and clear by way of example. We'll do 2 of these examples. What if you had a substance and you found out that the empirical formula was CH2O by the methods of the first 2 tutorials? Now you're given this extra information. The molecule actually weighs 120. Can you tell what the molecule's formula is? And you say, yeah, I'm going to figure out what this thing has as a mass, the CH2O, and then think of that like as a building block, like a brick of the actual molecule. And then just ask myself how many of those bricks are in the actual molecule. Let's try and actually look at it. So here's this thing I'm trying to get you to imagine like a brick. It's CH2O. I know the actual molecule, to have this empirical formula, has to be some multiple of this particular substance or this particular brick. What's this thing weigh? 12 for the carbon plus 2 more. For the hydrogen is 14 plus 16 for the oxygen. This thing weighs 30. So you can kind of tell just by glancing at the numbers how many 30s are there in 120. Well, 4 of them. So there must be actually 4 bricks in the final molecule. But just to make this kind of painfully obvious, if we had 2 bricks, would they still have the same ratio of 1 carbon for every 2 hydrogens to an oxygen? Sure. You'd actually write this, though, as C2H4O2. So that'd be one possible molecule. You say, yeah, but that doesn't weigh enough. It would only weigh 60. C3H6O3 would be the formula for this. No, that's not the right molecule either, because this would only weigh 390. Finally, sorry about that. 4 of these weighing 30 apiece would weigh 120. That's the right thing. That's the right formula. We found it. It's C4H8O4. So these are the possible molecules that would have a ratio of 1 carbon to 2 hydrogens to an oxygen. But given their masses relative to this mass, we know that the last one is the final answer. Of course, on a quiz, you don't sit there and draw these molecules out. You just do this math. I'm just trying to make sure this math, which is as simple as can be, makes sense to you. You're going to take the molar mass given, 120, and divide by the mass of what the empirical formula represents, 30 in this case. And that should make sense to you now with these pictures that when I divide 120 by 30, the answer is 4. There must be 4 of these empirical formula bricks, I'm calling them, in the actual molecule. So typically it's written down here like this. You write down what the empirical formula represents, and you put a little sub 4 there. You wouldn't leave it like that because that's kind of a mistaken way of writing. It makes it look like there's this structure in here 4 times repeating. We don't know what the structure is of the molecule yet, but the actual formula would be C4H8O4. All right, let's have a look at another one, almost exactly the same. This time, same exact molecule, but the thing, empirical formula, but the molecule weighs 180. What's the formula? I think you can see it without all the drawing. This thing we said weighed 30. 30 goes into 186 times. So what's the molecular formula? C6H12O6. Let's do that nice and slow to make sure that we see it. What's the brick weigh? 30. How many bricks are there? Well, let's have a look. It's got to weigh 180. This thing weighs 30, 60, 90, 120. Finally, we got there. Did I do it right? Yes, 150 and 180. It just took me a little while. 180. So the molecule's formula is C6H12O6. What would you actually do? You would take the 180, divide by 30 to get 6. And then this down here is how you would think about it if you have to write it out at all. Multiply out all this, the subscripts by 6 to get C6H12O6 as your final answer. Okay, hopefully that was pretty good. Let's look at a more realistic example now. So here you have this thing called ascorbic acid, vitamin C, and you analyze it by the methods that we've done so far. You would do a combustion analysis and find out the empirical formula, or you'd get these mass percents. So let's go through the calculation, and at the end let's do this extra part. It's but since I'm given the molar mass, I'm going to divide what the empirical formula represents into 176 to figure out the actual formula for the molecule. So step by step, the same step we've done before. Write out the mass ratio, divide by the respective molar masses. We know how to do this. Divide by the smallest number, that's the 3.406. You get a ratio of 1 to 1.33 to 1. You recognize that that's the same as 1 1/3, so you multiply out all the numbers by 3, and you get an empirical formula, C3H4O3. Now you say, okay, what does this thing weigh? That represents like the brick in the final molecule. It might actually have a formula of C3H4O3, or it would be 2 of those bricks, or 3. So I'll find the weight of this substance here, and then divide that into the actual weight of the molecule, the actual mass of the molecule. So let's do it. So here's the possible bricks again, 1, 2, 3, etc. We don't have to go very far. We recognize that this is the right answer by actually working out the mass of what C3H4O3 represents. Turns out to be 88. How many 88s are in 176? 2. So therefore this must be the right structure of that, or the right formula for that molecule, C6H8O6. I feel like that's it. I feel like I rushed a little bit at the end. I'm not sure. So let's just look at the final answer. This is the empirical formula. The molecular formula actually contains 2 of those units. How do I know that? Because I find the mass of the empirical formula and I divide it into the mass, the molar mass given, which has to be given to you independently to get the final answer. That's it. This probably felt slightly long-winded to you in terms of just an algorithm. I could have told you this in 2 seconds. Do exactly what I just said. Get the empirical formula. You know how to do that. Divide the final weight of that empirical formula, what it represents, into the molar mass to get the molecular formula. So we could have said that, but I just wanted to make sure you understood at least kind of the logic behind it. All right, that's it. Good luck with this, and you know, we're practicing class like always. And if you have any trouble with it, but I think you'll be okay. Great. See you then. Thanks.